Aloha! Welcome to our exploration of classical statistics in the era of big data. As technology advances, our approach to data analytics must evolve. Today, we'll dive into the relevance of classical statistical methods. We'll particularly focus on the p-value's role in modern data analysis. Let's begin this insightful journey. Classical statistics emerged when data collection was expensive and time-consuming. Researchers often worked with small sample sizes. Methods like hypothesis testing and p-values were developed to draw conclusions from limited data. These tools helped generalize findings to a larger population. They were essential in an era with constrained data resources. The p-value is a cornerstone of classical statistics. It measures the probability of obtaining a test statistic as extreme as the observed one. This is under the assumption of repeating the study infinitely. In small sample contexts, this hypothetical was crucial for drawing conclusions. It accounted for variations due to chance in limited data. Today, we have access to massive datasets with millions of records and thousands of features. This abundance changes the statistical landscape dramatically. The question of repeating studies hypothetically and infinitely loses its relevance. We can observe patterns directly with high confidence. The need for theoretical constructs like sampling distributions is less important. Imagine having just $10 in your pocket. You wonder how life would be with more money. But with $10 million, you don't need hypotheticals. You can directly enjoy your lifestyle. Similarly, vast datasets allow direct analysis without relying on theoretical probabilities. Big data introduces complexities that p-values struggle to address. Datasets often have numerous variables, leading to multicollinearity. The sheer number of tests can result in false positives. Adjustments are needed, but they're not always straightforward. Traditional methods fall short in accommodating these complexities. Big data often violates the assumption of independent observations. Social media data, for instance, is highly interconnected. One data point may influence another, creating dependencies. Classical p-value logic doesn't handle these well. New methods are needed to address these dependencies effectively. In 2014, a study analyzed social media inputs' effect on human behaviors using a massive sample. The sample size was 689,003, and p-values were extremely small. However, with such a large sample, these p-values lost meaning. In response to another experiment using 61 million Facebook users that reported significant p-values, a researcher wrote, "A data set that was millions of lines long was analyzed with the 100-year-old t-test, which had been created primarily to deal with a problem of small sample size. This highlighted the limitations of traditional methods. It sparked discussions on the need for new approaches in big data contexts." While p-values have their place, their limitations are evident in big data environments. They were designed for small samples, not vast datasets. As data grows, the need for new statistical methods becomes clear. Researchers must adapt to these changes. It's time to rethink classical statistics in the modern age. Thank you for joining us on this exploration of classical statistics and big data. We hope you found it insightful and thought-provoking. Stay tuned for more engaging content. Maloha!